Good, so I'm Ryan Gates, and this is my Standing Waves project. For this, we will be using my iPod with calculator, some paper for calculations, and a tape measure, which is currently on the ground. I'm here in a practice studio in the conservatory basement, so we're going to find the standing waves three standing waves that fit within this practice studio. Now, a standing wave is a wave that can fit exactly between two parallel surfaces in a room. So if it'll reflect off of each wall and then go back over top of itself. And these are bad because it can cause intonation problems and it can cause distortion in certain frequencies. And that's not good to have in a recording studio. So, and when the waves cross over each other, they create things called nodes and antinodes. Nodes are the places in the waves where there are absolutely no movement, and antinodes are the places that have the maximum amplitude. So we're going to figure out the waves, the standing waves in this room right now. First off, we're going to measure the dimensions of the room. So I'm going to take 3 dimensions, the parallels between 3 sets of parallel surfaces. The first set will be this wall that is in front of me, and this wall that is behind me, and then this wall, and then the ceiling and the floor. So first I'm going to get the length of between these 2 walls, which I already laid the tape measure out for it because it was easier to have that a little bit prepared before time. But so this distance between this wall in front of me and this one behind me is 8 feet 4 inches, or 8 1/3 feet, which I'm just going to round off to 8.33 feet. Now, putting that in the equation we're using, and this equation we're using is going to be the frequency of the wave is equal to the velocity, which we're going to assume is 1,130 feet per second, over the wavelength, which will be the length that we measured. So it'll be F equals 1130 over 8.33 feet. So the first equation will look like that. And let's get some other ones. Now the measurement between these 2 walls is about 5 feet 9 inches, which is 5.75 feet. And so we plug this into this equation to where F equals 1130 over 5.75 feet. And now we measure from the floor to the ceiling. And that measurement was roughly 8 feet 9 inches, or 8.75 feet. So we plug that into a third equation, which is F equals 1130 over 8.75 feet. And now, all that's left for us to do to find the standing waves is to work out the algebra in the calculations. And so for the first one, 1130 divided by 8.33 is a really long number that I'm just going to round off to the first decimal point. So it'll be 135.7 hertz. Now that's the standing wave that exists between this wall in front of me and the wall behind me. And for the second one, which is this wall and then this wall over here, is 1130 divided by 5.75 equals 196.5 hertz. Now that is the wavelength that exists between of the standing wave that exists between these two. Or I'm sorry, not the wavelength, but the frequency. And now it's between the floor and the ceiling. So 1130 divided by 8.75 feet equals 129.1 hertz. So, to recap, the frequency of the standing wave that exists between these two walls is 135.7 hertz. The frequency of the standing wave between these two walls is 196.5 hertz. And the frequency of the standing wave that exists between the floor and the ceiling is 129.1 hertz.